So thank you all for coming. My name is Andy Yan. I understand there's some people here who are part of the Neuroimaging Initiative community. There are others who are students taking this for credit, right? A few of you? Yeah. So just so you know, this talk is geared towards a couple of different audiences. I want you all to get something out of it. I'll be talking about a different neuroimaging method. Maybe you've heard of it. We're talking about diffusion-weighted imaging analysis. But this is a hybrid of both a lecture and a practical. And I'm recording this for people who want to use some of these tools I'm going to be talking about. That's a main part of my job. So if some of these things seem a little bit over your head, I will try to give you enough background to follow along. But be aware that this is part 2 in probably a 3-part series on diffusion-weighted imaging analysis. So I'm already assuming that there's some background and some technical skills are known. That being said, feel free if you have any questions about what I'm discussing, please ask. So as I mentioned, the first part of this was in the early part of August, first week of August. And back then, we did something called diffusion tensor imaging. And I want to clarify right off the bat some of the terms we're going to use, because some people say that they collect DTI scans. That's not technically true. We collect diffusion-weighted scans, and then we have options about what we want to do with that afterwards. It's a technique for mapping white matter tracts primarily. And one thing that we can usually do is called diffusion tensor imaging, which is fitting tensors in each of these voxels of the brain. And once we do that, we can have some sense of what the orientation is of the fibers and how strong that directionality is. Today's agenda is going to be a continuation of our analysis of diffusion-weighted imaging, but it's going to be giving you another option for how you want to analyze diffusion-weighted imaging data. So before we talked about DTI analysis, and today we're going to be talking about a new package called MRtrix. And in my opinion, I think it overcomes some of the disadvantages that DTI analysis has. It has some very good properties. It's a new way to look at your data. And for the people who do have diffusion-weighted data, I recommend it as another perspective. So I'll be comparing MRtrix to TBSS, and in particular, I'll be addressing something called the crossing fibers problem, which you probably read about in that paper. That's been something they've known about for a long time. Diffusion-weighted imaging has been around for probably since the early 90s is when they first started doing it. And the past 15 years it became very, very popular. But they've known about this problem for a long time, and MRtrix has some algorithms to deal with it. And lastly, I'll be talking about some advanced DWI protocols. If you haven't used them already, I'll be talking specifically about multi-shell acquisition and why you may want to use that for acquiring diffusion images. Also, I thought John Plass would be here, but I wanted to give him credit because I've been talking to him quite a bit. I've only used MRtrix for the past few months, but John has a lot of experience with it, a lot more experience under his belt. And I just wanted to thank him because I've used at least one of his images, and he's clarified a lot of concepts for me. So I was hoping he would be here, but that's okay. Okay, so to give you some background about what we're dealing with, you've probably already come across magnetic resonance images, right, and some of what we've talked about so far. These are essentially images of the brain. They're non-invasive, but we can construct them by using some properties of magnetic resonance physics. Now, this looks similar to those images, but with diffusion images, we do something that's a little bit counterintuitive. This is a diffusion image, and where there is a little bit darker signal or greater signal loss, that indicates where there is greater diffusion. It's a little counterintuitive, but I'll explain why that is in just a second. So I'm going to first give a couple of images about how these are created, and then show you an animation, putting it all together to give you some sense of how all of this is related. So first, imagine that these circles represent these hydrogen protons in the body. So I'm going to give a pretty fast summary of what's going on here. With magnetic resonance, we're primarily interested in hydrogen because that composes a lot of the protons in your body. And they have this intrinsic property called spin. So think of them as tops, and if we're looking from the top down, you can see them spinning around a certain axis. Now, with our magnet, we can elicit these things called excitation or radio frequency pulses to turn the direction of the spins onto a perpendicular plane, perpendicular to the main magnetic field, which is very strong and it's always on. But with diffusion imaging, we add a little twist. We have these things called dephasing and rephasing gradients. So initially, with this very strong homogeneous magnetic field, all the spins are roughly in the same direction, okay, precessing at the same rate. But if we dephase it, we can have a gradient which is, say, stronger at this end of the scanner and weaker over here. And there's a function of spins where the stronger the magnetic field is, the faster they are going to precess. So if it's stronger over here, they're going to be spinning faster. If it's weaker over here, they're going to be spinning slower. Make sense so far? All right. So we do that to dephase them, meaning that now they're all going to be not spinning in phase like they were here, but out of phase. But we can also apply a rephasing gradient, which is an equal and opposite gradient from the dephasing gradient. And after that's done, everything is going to be back to what it was before we did anything. Okay? I'm also going to briefly talk about b-values because that will come back up when I talk about multi-shell acquisition. So I'm going to give, this is the only equation I'm going to give. I'm not that crazy about equations, but it is important in this case. We have these things called b-values to modulate the amount of diffusion signal that we get. And a b-value is a property of a few different parameters, and a few of them we can control. One of them is g, which is the height of that diffusion gradient. Okay, so how much it's going to cause these things to go out of phase with respect to each other. There's small delta, which is the time that we have this gradient on. And then there's big delta, which is the time between the onset of the dephasing gradient and the onset of the rephasing gradient, also known as mixing time. So the longer this is on, the more chance there is for something called diffusion to happen and to weaken that signal. Lastly, this thing is a constant. It's called the gyromagnetic ratio. I'm not going to focus on that too much. In a 3 Tesla scanner, you don't really have many options to change it. Okay, so this animation I'm going to show you, this is not mine. I did not make it, but I think it's very informative. It's from USC, and originally they had a voiceover for it. It was, oddly enough, it was like a robotic woman's voice. It wasn't a real woman's voice. I don't know why they couldn't do that, but they chose to use a robot. So it's kind of strange. Okay. I don't have that audio here. I'm going to be giving you my own voiceover for what's happening. But I do think it links together everything we've talked about so far. So imagine these are all the proton atoms. Okay? Originally, they were aligned with a magnetic field, but we have a radio frequency pulse that puts them into another plane. Now we have this dephasing gradient, and you'll notice that it's going to be a different strength in one part of the scanner than it is on a different part of the scanner. So if you pay attention, you'll notice that these protons over here are starting to precess more rapidly than the ones over there. It's a gradient. It's usually a linear function where it's stronger here, weaker over here. Now the second part that we do is we then have a dephasing gradient. So right now they're out of phase. They're faster over here. They're slower over here. But if we apply this equal and opposite rephasing gradient, what's going to happen at the end of that gradient is they're going to be where they were before we did anything. It canceled out what we did. Right? Now that's all well and good if everything was staying in the same place where it was. But what usually happens is after we apply our dephasing gradient, there's some diffusion where these hydrogen protons are going to be randomly walking around according to the principles of Brownian motion. So now, after we do our rephasing gradient, it didn't cancel everything out and bring everything back to the state it was in the beginning. Because there's been diffusion, now if we took a signal from here, if there's a lot of diffusion, there's going to be some signal loss. Now these parameters that we can change, I'll show you how these are related to the diffusion signal that we get in this B value. Okay. So the first thing that we can change is the height of that gradient specified by G. So if we made it a little bit shorter, it's going to induce less dephasing because it's not going to be as strong there as it is over there. Another parameter we can change is that small delta, which is the duration that the gradient is on. So the amount of time that we have for all these spins to be dephased. So if we change delta to be very long, there's more opportunity, there's more time for the dephasing to happen. So if we had that be longer, there'd be more diffusion, correspondingly less signal. All things being equal. And the very last parameter we can change is big delta, also known as mixing time, which is the difference between the onset of the dephasing gradient and the rephasing gradient. The three things that we can change. So you can get different B values in different ways. And it's a very important principle of diffusion because, one, it's something that you do have some control over. And if you acquire your data at different B values, you get something called multi-shell acquisition. And that's an important property I'll talk about later. OK, any questions about this so far? That's the background that I'm going to be giving, and then most of the rest is talking about MRtrix. Yeah?
So the greater the delta, the greater the mixing time, the more opportunity there is for diffusion.
Exactly, yeah. So all things being equal, if you increase big delta, you're probably going to get more signal loss, indicating more diffusion, yeah. OK. So last month, we used a package called TBSS, or Tract-Based Spatial Statistics. And that used that DTI approach I was talking about. So let me define some of those terms so we get a clearer contrast of what's going on with MRtrix. With DTI, we have a couple things, eigenvectors and eigenvalues. So all that diffusion that's happening, we can fit a mathematical model to represent what that looks like. So if there was no preferred diffusion along any of the directions, it would be best modeled by a sphere, indicating that there's no preferred direction of diffusion. Now, in the brain, and specifically in the white matter tracts, along these axons, they're like tubes, right? It's like a garden hose, and obviously the water is going to be preferentially going along one part of the tube. Now, with axons, it's a little bit different because we're assuming that it's basically just randomly diffusing. But if you constrict the direction that it can diffuse, it's going to preferentially go along the direction of those boundaries. So we could model it with something like this, where it's a little bit more oblong. And depending on what the direction was of the diffusion, we can model that. And we can also model the magnitude of the diffusion. So if in a particular voxel that we're measuring signal from, there are some white matter tracts and they're all oriented in the same direction, you're going to get a high eigenvalue representing the magnitude, and the eigenvector is going to represent the direction of that. One parameter that you also have control over when you're doing a diffusion-weighted imaging scan is the number of directions that you want to sample from. So some people have maybe a few dozen, others can sample 100 or so. Kristen, I don't know what people typically do around here, the number of directions for a scan.
I'd say anywhere from 64 to 102, roughly.
64 to 102, that makes sense. Yeah, so there'll be, what that means is that you are applying those gradients at different directions, right? So you're trying to get as much angular resolution as you can. Because if you can do that, you get finer maps that actually trace out what the directions are of these different white matter pathways. Now, where we left off before was we looked at these tensors that were fitted, right? So that model I was just showing you, this is what it looks like in the brain. This is zoomed in on a particular tract. And the color coding scheme is the same for both TBSS and for MRtrix, as I'll show you in a little bit. It's red going from left to right, it's blue going from top to bottom, and it's green going from back to front. Which is why I always recommend, as part of quality control, to check these maps, either the fitted tensors or, as we'll see in MRtrix, the fitted tracts, to make sure that the major tracts make sense. So with the corpus callosum, obviously it should be primarily red because the fibers are going mostly from left to right. If it's green or blue, then something might have got messed up. But that's one of them. A couple of the other ones are the corona radiata. It's primarily blue because it goes up and down. And I check either the superior longitudinal fasciculus or the cingulum bundle, right above the corpus callosum, which primarily goes from back to front. If those check out, probably it did a pretty good job throughout the whole brain of fitting the tensors. That's my approach. Other people may disagree. Some people prefer to look at each orientation volume separately to make sure that it looked at the orientation that it was supposed to. I consider that a bit of overkill, but again, people may disagree with me. So moving on to MRtrix. Recall that the major problem that people have known about for a long time with diffusion tensor imaging is this so-called crossing fibers problem. So let me explain what that means. If I measure diffusion signal from a single voxel, and I have one fiber orientation going this way and another one going this way, the tensor that I'm fitting is going to split the difference and essentially say that there's no preferred diffusion in any direction, even though we know that that's not the case. It's almost as though these two orthogonal directions cancel each other out. It's usually not that extreme, but you get the point. There are a lot of crossing fibers in the brain. Some people estimate as many as 90% of the voxels that we're collecting have some kind of crossing fiber. So if we want to recover what the fiber orientations actually look like, we need to adopt a different approach. And I'll show you how MRtrix does that. MRtrix is a software package for diffusion analysis, and the way it's going to address this problem is through a couple of different algorithms. One is by measuring the fiber orientation density, and the second is to recover that by using a procedure called spherical deconvolution. This looks similar to those tensors that I showed you before, but there's a critical difference, which I'll show you in a couple of slides. I'm going to break out in a little bit and show you a demo of a few basic commands that MRtrix uses to show you how we're doing all of this. But a few more words about MRtrix. I really like this package because it's been around for a while. And it's not always clear with a bunch of different neural imaging packages which ones are going to have staying power. Sometimes they're supported for a year or two, then they go away. Either the people just move on or they're not supporting it anymore. So MRtrix, it's been around for a while. They've been publishing about the concepts for about 10 years, and I think it's been around for at least 5 or 6 years. But it's a very robust community. They give a lot of support. They got a good message board, and they release updates frequently. So I really like it. Okay, and when I'm showing you some of these MRtrix demos, just to be clear in the terminology, they have a library of commands, and thankfully they are labeled in a very logical and consistent manner. You'll notice that the commands have these prefixes and suffixes indicating what data type they're manipulating. So if they begin with DCM, DWI, MR, that indicates what file type or what data type it's going to be manipulating. So DCM stands for DICOM. It's a raw neuroimaging file. DWI, diffusion weighted images, and MR, magnetic resonance images. The suffixes will give you some idea about what process is going on. So for example, convert, generate, threshold will tell you what exactly that command is going to be doing. So if you see a command like DWI to FOD, that's an operation to convert DWI data to this fiber orientation density data. And just to quiz you, what do you think that MR convert does, if you had to guess? You know the answer to run? Okay, that's fine. It converts MR data to another format. So typically, if you had something in NAI format, hey, that's the name of our organization. I just realized that. If you had something in neuroimaging, now I'm confused what that stands for. NIPTI, Neuroimaging, Neuroinformatics Technology Initiative. Okay. That's a common extension for neuroimaging data. But MRtrix likes to work with its own extension, which is .mif, MRtrix format. Okay, so I'm going to give you a brief demo of MRview, which we'll be using later on to look at how tracks are fitted and to compare it to the tensor fitting that we did last month. Every neuroimaging software package has its own viewer, right? Because you'll be manipulating data, you'll be doing different processing steps, you'll need to check it. And in my opinion, some are better than others. MRview is pretty good. In this directory, this contains a lot of the data that we had processed at the very end of our workshop back in August. So this may look familiar. I'm using one of the subjects from that data set that we were working with. We're not going to be doing a group analysis today. We just don't have the time. But I'll show you how we can do a lot of the pre-processing for a single subject. So you'll notice, what are some important things to point out here? bvals is a file containing the b value, that thing we were talking about earlier, for each volume that was acquired. bvex indicates the actual orientation of the acquisition that happened. And at the end of our last workshop, this right here, this sub-01 preproc, was one of the final images we created that it had denoising and also eddy correction done to it. Not going to get too much into those, but we're just cleaning up our images, basically. Okay, so if I open up MRview, it's a pretty clean format. I like it. Pretty typical, so you can open any one of these images. Let me open up sub01 preproc.mif. I'd already converted that one. This data isn't great. I didn't have what's called a reverse phase-encoded image to do something called unwarping, which would recover a lot of signal in this orbital frontal area. You should collect those if you can. I'm dealing with publicly available data. They didn't have it, so wasn't able to do that. But this is what a typical diffusion image looks like. You can pan around. You can do different views. Ortho view, where you have an orthogonal slice, sagittal, coronal, axial. And something we'll be using a lot is this tool command to both change the viewing options and also later on look at the tracts and some of the fiber orientation bundles as well. So these are pretty common steps that I'm going through. Things like modifying the scaling to make these pictures a little bit easier to look at. And notice that for our diffusion data, we have several different images that are concatenated together. Remember all those directions I was talking about? We're going to have one volume for each of those directions that we acquired. So if I go through this, it's a little bit darker here. That very first image was called a B0 image, where there was no diffusion applied. Okay, we usually use that for co-registration purposes, baseline purposes. and the other ones tend to be a little bit darker, but we can modify our intensity threshold right there. So this is pretty basic, just to look through, get a sense of what's going on. This is also a very useful tool to use, where you can here we go, change the actual orientation that you're looking at. So you can see these two images over here sliding around. This is important if you want to look at a specific orientation direction, let's say, to make sure that it did the diffusion along that particular direction. If things get too crazy, just press R and you can go back to the normal mode. Okay. So those are the basics. We'll be getting into some more advanced ones as we create more advanced data. Okay, so here's the crux of the matter. Here is how MRtrix proposes to fix this crossing fibers problem. It's pretty ingenious when you think about it. Their terminology for what they're looking at is a fixel instead of a voxel. That's a specific fiber bundle within a voxel. Now, a voxel is the smallest resolution element we have in those images. And at first, when I was hearing about this, what really tripped me up, I was thinking, we only have a single voxel. How is it possible that we can reconstruct what the fiber orientations look like? It's kind of crazy, right? I mean, how do you get more detailed information than what you just see in this grayscale intensity image? But what they do, well, what we do every time that we collect DWI data, is we're acquiring at multiple different orientations for that same voxel. So we're getting a sense of where's there more signal loss at which orientation. So what can we then infer about what the diffusion is like, how strong it is, and then try to reconstruct what the original fiber orientations look like. And we're going to do that with something called a basis function. Basis function, we do that a lot. Well, we do it all the time in fMRI analysis because we have these very complex signals that we assume are composed of simpler signals. We model those as basis functions. So this thing over here that I have labeled as A, this is an image I got from John Plass, actually. So maybe he stole it from somebody else, but I'm going to give him credit because I don't know where he got it from. But A, think of that as the raw diffusion signal that we're getting from a single voxel. Looks kind of weird, right? Looks kind of like silly putty. What do we make of this? Well, it's a complex signal that we can assume is composed of a linear sum of these simpler orientations. So this basis function I have labeled as R, or John labeled as R. And if we convolve that with these different orientation directions, we can reconstruct the original signal. Let me give you a slightly different perspective on this. Oh, and this is the command we're going to be using. They call this basis function right here tournier. It's named after Donald Tournier, which is one of the developers of MRtrix. Just as with fMRI data, we do have a small selection of basis functions we can choose from, but usually we choose the gamma one because it's the simplest, and it may not be right all the time in every case, but it does a pretty good job. So brief detour into basis functions with fMRI, because if you know about basis functions with fMRI, you'll have a peg to hang this on. If I'm looking at your auditory cortex, obviously we know that the auditory cortex is responsive to auditory stimuli. That seems to be what it processes. And with fMRI data, we're looking at something called the hemodynamic response function. That's a stereotyped response of these voxels we're measuring signal from. Right? So how the blood flow should play out over time. Again, it's not always a perfect representation, but it's a pretty good model, so we use it quite a bit. So if I give you a stimulus, represented right here, it's a punctate instantaneous function, we should get something looking like this for the hemodynamic response. Right? There's blood flow that comes in, it increases the signal, it decays over time, and if we had fine enough resolution, we would assume that it looked something like that. We use that to construct models of how we think the activity should look. Now, if we have multiple basis functions or stimuli that are happening within a very short time window of each other, we can create more complex signals. This is called convolution. So notice there's one here, there's another one here, there's another one here, and in blue that's contributing to this very complex signal, but in fact it's actually a summation of these other basis functions right here. Okay. In fMRI analysis, we would then try to estimate what the actual height of these HRFs were to each of these different conditions to try to best fit the original signal that we see. So translating this to diffusion data, we have this pretty complex diffusion signal from a single voxel that we assume is constructed from a bunch of these fiber orientations in all different directions. But we try to decompose it using a single fiber orientation but in different directions. Then we add those up to get the original signal. Clear as mud? Yeah? Okay. Yeah?
And there's a unique solution? Or there's a unique addition of basis functions that will produce the signal in that function?
There's some error term, probably, but I mean, if you used enough, obviously. I think it's constrained by the actual number of directions that you collect, though. Yeah. So you can't add more directions than you actually have to try to reconstruct the signal. But from what I've read from their papers, it seems to do a pretty good job at recovering the ground truth of what's going on. Yeah.
Another way of approaching the crossing fibers problem is, if you've got a fiber going through a voxel, that fiber, of course, is not just one voxel in length. It's got length associated.
Exactly.
Say if you looked at the adjacent voxel,
Yes.
and the fiber was actually going in that direction, you ought to be able to detect it in the adjacent voxel as well.
Right.
Dot, dot, dot.
Yes.
And so can't you disambiguate the crossing fiber problem by making use of more than one voxel's worth of information at a time?
Yes, you can do that. You can impose certain constraints to how you're going to be estimating the direction and the density of the fiber. I wanted to say amplitude, but the density. So you can do that a couple different ways. You can do that with something called anatomically constrained tractography, which is using information from nearby voxels to basically constrain where could this system of fibers logically terminate, right? So it will try to remove biologically implausible connections and terminations. Yeah, it's a more advanced technique. I'll talk about it briefly. It takes too much time to do here in this setting, but it's not too tedious if you're doing this, outside on your own in a lab. Yeah, or using a more advanced computer. I have this 2012 MacBook Pro, which is pretty good, but it's a little bit behind the times. So I'm going to show you that basis function and also another step, which also very similar to fMRI analysis, which is to create a mask to constrain your analysis. Now, really, we do this for computational purposes, right? We don't want to analyze things that are way outside of the brain, even though we collect a field of view which incorporates a lot of non-brain voxels, mainly to speed up our processing and to constrain our analysis. So let me show you these two particular functions. Okay. The first one that I showed was DWI to response using that tournier basis function. The process diffusion data is called sub01 preproc.mif, and then I'm outputting it into this response.txt file. For all these commands I'm going to be going through, I've appended this force command to overwrite anything that's already in the folder. Don't pay too much attention to it. It's just to make sure I don't get stuck with any file already exists errors. It gives me a warning, but it's not going to crash out. So this takes not too long. And something that's a little bit different from fMRI analysis is it's using It's not using all of the voxels that were sampled, but it's using some of them to try to construct a basis function appropriate for that subject. So usually with fMRI analysis, we have this mathematical formula representing our HRF basis function, but it's not derived from, say, the single subject that we're analyzing. You can do it theoretically. There's a package called FLOBs and FSL if you want to make your own subject-specific HRF, but we don't usually do that. Their default in MRtrix is for you to do that. So it takes the data from that subject and it uses that to construct a basis function. Yeah.
So each subject has a different basis set?
Slightly, yeah. They're not radically different, but they are, yeah.
Do you know why? What's the advantage of that?
I'm not entirely sure. They seem to say that it gives greater specificity, maybe more power. These things don't look that different from what I've seen, but they are modulated at each voxel to try to best fit the data. I'm not sure exactly what they're trying to look at within each subject, like what actually differs with this basis function. I'll show you what it looks like, actually. I'm using a different viewer just so you know. So again, this looks like a donut. Notice that it has these orthogonal axes. So there's our x, there's our y, and there's our z, I believe. Left to right, back to forward, and bottom to top. So what's going to happen at each voxel is it's going to be elongating this along the different axes. So if, for example, I have this basis function within my corpus callosum, it's going to extend it, it's going to stretch it out along the x-axis. It's going to look very, very strong and big. I don't know. I'll show you what it looks like. But it's going to be primarily along that axis, but not along the others. But the benefit of this is if there are crossing fibers, it can elongate along the other ones as well. So you're getting a finer representation about what all these different crossing fibers might be doing within a single voxel. Okay, the next thing here, I just have all my steps written out because I can't remember them, is DWI to mask. Again, not very complicated. We're just trying to get rid of non-brain voxels. Yes?
You said it doesn't use all of the voxels, that you collect just a certain number. Does it determine that based on how concentrated the fibers are, or is there just a default number of voxels? Because I feel like the highest resolution image would
Right.
have an infinite number of voxels. So I don't understand.
Yeah, no, that's a good point. From what I remember reading, they do have some algorithm to try to select representative white matter voxels. I'm not sure exactly how they do that, but it's not as though they would accept candidates from, say, the ventricles, I believe, yeah. I may be remembering that wrong, but I don't think it's a completely random selection process that it does to generate the basis function. Okay. So I'm going to load these masks just to give you a brief overview of what these things look like, and to give you a couple of different examples of what can go wrong. So this first mask that I generated, you'll notice there are pretty big holes. You may think that these are maybe in the ventricles, but actually they seem to extend a little bit more. There's a procedure called bias correction, and I should post these steps that I used, but basically you want the mask to cover as much of the brain as possible for when we're doing the rest of our steps. I don't have time to get into that, so I won't, but just be aware that if you're seeing these big holes in that mask, you might want to apply bias correction. Okay, now moving on to the meat of the project, which is constrained spherical deconvolution. So remember, we're using this basis function to try to deconvolve this more complex signal into a series of fiber orientations along certain directions. We'll do this with a command called DWI to FOD. and using that basis function and also specifying the mask we're going to be using. Now after that, we're going to be generating maps and tracts using TCK or TrackGen. And what this is going to do is it's going to randomly seed fiber beginnings in different parts of the brain, right? And it's going to then generate a map of what are the primary tracts, and later on we'll be able to use this with a command called track-to-connectome if you have a gray matter parcellation to see which parts of the gray matter seem to be most highly connected to the other ones. So let me run those and show you what those look like. Again, these are not very sophisticated commands. It's really just understanding some of the principles behind it, which takes the most time. So DWI to FOD takes a fair amount of time. What was I going to say here? Notice that I'm not doing anatomically constrained tractography. This is something that John alluded to earlier. So during this part of it, if you wanted to, you could provide a command which inputs these different tissue types that you have in your brain so that this knows where those tissue types are, and it will try to generate more biologically plausible tract orientations. Yeah, Sean.
Do you have a link of where you got these command lines from, like for a tutorial?
Yeah.
It's really a lot.
It is, yeah.
Contemplate what's going on.
Right. Yeah. So first of all, I will have these slides posted online soon. Second, on the MRtrix website, they do have a pretty extensive documentation about, especially if you're just starting out, what steps you will need to do to get your data ready to start fitting these tracks. Yeah. So I'm basing a lot of these on that. Some of the commands or some of the options weren't appropriate for the data I was looking at, so I had to modify them. But if you had, say, bias-corrected data, you would use one option as opposed to another. If you had your tissue types generated from something like FSL's FAST, I would definitely use that, because as you'll see, these tracks are going to seem a little bit, it's going to seem a little bit too dense of coverage. It's not going to have any boundaries really, right? As opposed to if you had your anatomical constraints, it would look a little bit cleaner. Yeah, everything I have here, I mean, this is something I just have for reference so that I can copy and paste everything quickly. Let's see here. What else did I want to run here? Let's take a brief look at how these fiber orientation densities look. So I can open a file. I believe I called this one just FOD. And then I'm actually going to overlay that again on top of that because that image had a fair amount of anatomical coverage. Come on. Why is it not appearing? Oh, sorry about that. Right, so at this point, if you wanted to see those actual fiber orientation densities, you'd go to ODF display, click on this, and then I'm going to overlay it FOD again. So again, not anatomically constrained. It's going to look a little bit messy. But if I zoom in on some of the major tracts, you see that it did seem to do an okay job. I'm changing a few defaults just to make this easier to look at. You can change the scale, you can change detail as well. This really starts to tax my machine, so I'm not going to go too much farther than that. But again, this is similar to looking at those diffusion tensors I was looking at before, just to make sure that these tracts seem to follow the right directions in the major tracts where they should. And if it did that, that's a first pass quality control check that I would look at. So corpus callosum, some of the corona radiata. And if you want to, you can look at how this particular basis function was fit at that particular, yeah, right? It looks kind of weird, right? So this is a case where I am in part of the brain where it's primarily going down to up, which I would expect, but there is some evidence that there's some crossing fibers in the longitudinal direction from back to front. Look at something like the corpus callosum right in there. There's going to be virtually no deviation from this left to right orientation. Yeah?
In your previous tensor, why is there one side blue, one side red? How does that work?
One side blue, one side red?
Yeah, and then another green thing going here.
Right, so it's color-coded to try to best reflect what the orientation is. So if it was straight up and down, that would be the most blue. If it's a little bit offset to that, it's going to be color-coded slightly differently.
So you're saying that the tensor has an angle?
Well, this isn't necessarily a tensor, but yes, this is a fiber orientation model. Yeah.
Okay.
Yeah.
Your brain is not New York City.
Right. Yes.
It's not laid out as a brain.
Yeah. Exactly. Yeah. So in some of these voxels, it is going to be, probably pretty straight along one of those orthogonal directions. Other ones, it's going to be oblique, which we'd expect if we were sampling at all these different orientations.
But aren't these already deconvolved into the basis functions already? So
This is how it's being fit to it. So imagine that we had, like an fMRI data, we had like this signal that was being deconvolved, and then we modulated the amplitude of those basis functions. And this is showing us what the modulation is like along different orientations to best fit it. Okay, I'm just going to run through a few more, unless you have another thought. Okay. Let's see here. Okay, I'm going to get this one running while I talk on another slide. This is tckgen. So we take those that fiber orientation map. We're going to select a number of fibers that we want to seed throughout the brain, right? We're randomly doing this throughout that mask, and then I provide the output at the very end. How many tracks should you select? That's really up to you. 100,000 is typically what they recommend at the MRtrix website. But as you'll see, obviously you're going to get some measure of false positives, right? So some of these tracks that are being seeded may actually not represent, say, a track that actually exists. There's a fair amount of noise. You are going to have some false positives. And at some point in the future, we'll talk more about the thresholding, how you do this group analysis. And conceptually, it's very similar to fMRI data. But for now, I've got to force that. I'm going to give you a brief explanation for why this is going to be useful. So we had our fiber orientation density. And as part of that, as we did with the diffusion tensor images, which had measures of things like fractional anisotropy, mean diffusivity, different measures of diffusion, you can do whole brain analyses across subjects to test for where there are significant differences, right? So just like we did before, if it's a single voxel that we normalize to a common space across however many subjects we have, we could test whether something like FA is significantly different from zero or different between groups. So similar thing that you can do here with the orientation. But something else which people are probably more excited about is creating this thing called a connectome. It's a term that gets thrown around a lot. And in a couple different contexts, what we're going to be talking about here is using these tracked images in conjunction with a gray matter parcellation from a program like FreeSurfer to try and give some kind of quantitative analysis of which of these nodes have significant connections to each other. So you may have one gray matter node here, one gray matter node here, and based on these tracked maps that we generate, you can generate these correlation matrices showing the strength of the connection between them. These are used sometimes in, say, a clinical context if you're trying to examine where these connection patterns are different between, say, a clinical group, say Alzheimer's, OCD, schizophrenia, and some kind of control group. I know that somebody was asking about some of the uses of diffusion imaging. I unfortunately can't get too much into that, but that's, looking at, say, differences in connections is another, say, angle at diagnosing things like this. Yeah?
No, that was mine.
Okay, yeah. There's a paper I helped publish last year, which we were using DTI back then, but we used that in conjunction with functional connectivity, some structural analyses, to make the case that this group of subjects with mild traumatic brain injury, we kind of showed a convergence that in this part of the frontal pole, it seemed to suggest that the connections and also the cortical atrophy was disrupted there in that particular area. So that's a pretty heavy topic for another time. But this tract gen is probably complete at this point. No, it's not. Okay. Takes a while. Just so I have this recorded, and at some point I should put this up, this particular code up, because it's not, what I'm showing you now isn't written out explicitly on the MRtrix website. You have to do a little bit of digging, but it does work. Let's see here. I'm just going to put all these different lines here. So the first thing, if you want to constrain your tracts by these tissue boundaries, let's say, right? We know that the white matter tracts they should primarily be in the white matter, right? Not in the ventricles, not in the gray matter. They should primarily be in the white matter. So to constrain that, what we need to do is we need to have the subject's T1 weighted anatomical image. We need to co-register that to our diffusion data, and then from that, we need to use a command called 5ttkgen to generate 5 different tissue classes. The ones that they specify in MRtrix are, let's see if I get these, cortical gray matter, subcortical gray matter, white matter, CSF, and they leave an optional 5th class open if you want to identify any pathological tissue. So once you have those, when we do something like tckgen to generate these tracts, you give it this ACT option, you provide those tissue types, and then it will know where the boundaries are, where it can generate these tracts. So it's not going to do a termination out here or somewhere in a ventricle, because just by definition it won't be able to. A few words about multi-shell acquisition. I'll show you the finished product from TrackGen and then open it up to a couple different questions. Our job would be a lot easier if diffusion in the white matter tracts, these axons, was the only thing that we got signal from, but it's not. We also get signal from water from intra and extracellular areas within a certain voxel, and that contributes to the diffusion signal. So if you're considering creating a new protocol for a diffusion-weighted scan, be aware that it's impossible to disentangle what signal comes from which of these areas with only one B value. So if I had a B value of 1,000, then a B value of 2,000, a B value of 3,000. This is called a multi-shell acquisition. And you can see what the difference is between what theoretically you should get with a B value of 3,000 and a B value of 2,000. And that difference you can treat almost as a residual that you attribute to water from these non-white matter tract areas. I'm giving a pretty simplified overview of that. And Chrisanne, I don't know, is there what's the time penalty like for acquiring multi-shell as opposed to a single shell? Do you have any idea about that? Okay. Okay. Just curious. Anyway, we're nearly at the end here. And to show you these generated tracks, oh, there's one step I missed here. Shouldn't take too long. Once we've generated those tracks, created a map, I call this output TDI. Notice this looks pretty similar to those diffusion images we got before. But what you will notice if you do closer inspection is that with DTI, sometimes you'll get pretty abrupt changes in direction from one voxel to another. What MRtrix does is it tends to smooth out some of that, because now with these fiber orientation distributions, you can have basically tracks in multiple directions in a single voxel. And so it smooths it out a little bit, and according to their simulations, it gives you more accurate tract estimates between different regions of the brain. So I'm about out of time. This is all I had loaded for the practical. This will just get you off the ground. These are a couple checks to do, some pretty basic ones. And as long as you buy their logic for their use of their basis function, I believe it's a superior way to analyze the fusion data. So thank you very much for your time. I'll open it up to any questions. Thank you. Yeah, Taras.
Do you have a sense of how many p-values is overkill versus like?
I don't. If I had to, I would just be pulling a number out of my head.
But it's not like
It's-
two's a huge jump, and then
Right.
just that, how does that function look?
Yeah, right. How does the function look for? When do you start to get diminishing returns, right? Just my gut intuition, so take this with a grain of salt, is something like 3 or 4 is typically what I've seen. I haven't seen anything beyond that, at least not mainstream. Maybe there's like.
I'm not sure if like the biggest jump is from 1 to 2 or something like that. Where it's like,
Right. Oh, yeah. That's a good question. I don't know. I don't know what that function looks like. Yeah.
So, also on the same topic, have you read about multi-shell collection and why is there a connection to, like, you can calculate neurite density or even myelin density? Like, what's the connection? I mean, they're all white matter.
Yeah.
How can you use the multi-shell to estimate those little axons or protrusions?
Yeah. I'm just dipping my toe into the ocean as far as multi-shell is concerned. I haven't analyzed any multi-shell, so I can't speak too much to that, and I haven't read too much about that particular issue either. I'm assuming, obviously the more shells you collect, you should theoretically be able to make those finer distinctions like you were talking about. But again, I don't know, first of all, what B values are optimal, right? So is it 1,000, 2,000, 3,000, 1,000, 2,000, 4,000? I don't know. And how many shells I'm also unsure about. But something I do want to do soon is, I believe John has collected some multi-shell data, if I'm not confused on that. Or at least there is publicly available data from the Human Connectome project that I do know uses multi-shell. So that'd be good to compare to this. This is single shell acquisition, what I'm showing you right now. Like to compare the two. Yes? It's okay.
You mentioned there's 2 types that you can choose to analyze.
Yeah.
And like with the option of pathological tissue types.
Yes.
How is the program identifying the different tissue types?
Right. So with these weighted images, usually the different tissue types will have different intensities. And it tries to set different thresholds for, say, what's white matter, what's gray matter. Doesn't always do a perfect job, but they do it here. They do it especially in FreeSurfer, for example. Any type of segmentation that you would do, they try to identify some sort of threshold. More advanced ones will try to use additional details about the anatomy to determine that. So you may have a pretty, say, I don't know, relatively dark voxel in the white matter. But given the idea that, it's surrounded by white matter, it should also be white matter, it should not make the mistake of misclassifying it. Anything else? I think we're out of time. But thank you again. Thank you so much for coming.
Thank you.
Yeah.